Today we're going to be applying the concept of mass in 1 mole to figure out the composition or kind of what a compound is made out of based on its percentages, or to determine the percentages of a given compound. So we're going to kind of go both ways. And the first way we're going to look at this is through what's called percent composition. And that is defined as the percentage of each element in a compound by its mass. And if you think about percentages, we always define percent as a part over a whole. And so when we're working with the part, that will be each individual element, and then the whole will be the whole entire compound. And so if I were working with, I'm going to give an example that's not on our worksheet here, and then we'll do some that are on the worksheet. If I were to do water, because we've looked at that one a few times, just counting up the atoms, there's 2 hydrogens and 1 oxygen, so that's 3 atoms. That would be like 2/3 hydrogen and 1/3 oxygen if we're just doing it by number of atoms. Or we sometimes call that their molar ratio of the different atoms in the chemical formula. And so our percentages would probably be around 66% hydrogen and 33% oxygen. However, we need to take into account this last word here, by its mass. And so based on the periodic table, hydrogen's mass is only 1.01 and oxygen's is 16. And so if we have 2 hydrogens, that means our total hydrogen mass is around 2, and our total oxygen mass is 16. And so now our percentages are significantly different when we take into account the mass and not just the kind of molar ratio of the atoms in the compound. And so if I were to find the percent composition of each of these, my part, hydrogen, is going to be my 2.02, and my whole would be the whole water molar mass, 18.02. And then, of course, whenever we're finding percentage, we just add a little times 100 there. Otherwise, you will just be writing the percentage as a decimal, which is fine. But to make it easier for you, we're going to multiply them by 100 and have them as numbers between 1 and 100 rather than decimals. So we have 11% hydrogen, and if the whole thing is 100%, right, the whole composition, we could just subtract 11 from 100, and that would give us 89%. So we should have 89% oxygen since the whole thing is adding up to 100%. Let's check and see if that math works out. So we've got our mass of oxygen over the whole compound, and if we take 16 divided by 18.02 times 100, we get rounded up to 89%. I got 88.79 on my calculator, rounds up to 89. So there's my percentages. Those are a true percent composition by mass, and it's really important to take into account that molar mass so that we have the correct percentages. Notice it's not 66% hydrogen and 33% oxygen because of their significant difference in molar mass. So let's do 1, 2, and 3 are percent composition examples. Number 3 is most similar to what we just did, where you will take each of the elements and then find out their part and whole. I'm going to let you do this one on your own since it's really exactly the same as what we just did for water. The only thing you will need is just to double check your chemical formula is correct. So I would suggest writing it first and then checking it. But nickel 2 chloride is NiCl2. So again, just looking at the molar ratio of our atoms in this chemical formula, it looks like it's 1 to 2. So it would be like 1/3 nickel and 2/3 chlorine. But just like we learned in the water example, their masses are going to change that percent composition. So you will want to do percent nickel and percent chlorine based on their masses. Do the part over the whole, part being just the molar mass of the element, whole being the molar mass of the compound. So number 3 is just like what we did for water. Number 1 and 2 are slightly different. I think they're a little bit easier because they take out the element of the periodic table. So it's just giving you masses and a total, and so you're just doing part over whole, as given. So our percent carbon, if we read this problem, it says it's 1.95 grams carbon and the whole sample is 5 grams. So this would be our part, and this is our whole, each part of our elements. Now I went ahead and added these together and it does not equal 5, so we're going to adjust this here and make our hydrogen amount 0.47 just to make our numbers a little bit prettier and actually equal the total that is given. So our percent carbon is going to be 1.95 grams over 5 grams times 100. And that will give you 39%. Okay, so again, part over whole. This time it just takes out the need to use the periodic table. So you do hydrogen and sulfur, same thing, part over whole. And then number 2, same idea. This is part magnesium and part oxygen. So you need to actually calculate what the whole is for the compound by finding their sum. So that's pretty easy. Again, part over whole, you'll have 2 percentages for number 2. Now we have 2 more terms in our box at the top, and both of these describe a chemical formula. And the idea behind finding an empirical formula is that we are going to take percent composition information and kind of work backwards to figure out what the formula is. So if I were to say this compound has 11% hydrogen and 89% oxygen, what is its formula? We are trying to work backwards to figure out, oh, this is water, okay? And just like we talked about earlier, 11 and 89 does not really lend itself to 2-to-1 ratio, and that's because the percentages are by mass. So we'll have to turn that into a molar ratio by using molar mass, and that will tell us what the subscripts will need to be. So that we're comparing apples, not comparing apples and oranges. They're in the same kind of unit, taken out of their individual masses. So let's read these in our box up here. An empirical formula uses percent composition to determine an unknown chemical formula in its reduced form. So just like I said, if I have these percentages, to go backwards to the formula. The molecular formula is the true chemical formula of a compound related to the empirical formula by a scaling factor. So I actually want to define a scaling factor and show you this relationship by going to number 7. So if you'll flip to the back for me, number 7 does a really good job of showing us the difference between empirical and molecular formula. So the most important thing for you to remember is that empirical means reduced. Really, empirical means experimental, but it's going to be our reduced chemical formula. So we're going to fill in this table showing a relationship between kind of the reduced version, empirical formula, and then our larger version, the molecular formula, and by which factor it is related. And that factor is going to be multiplying between the two. So first example, let's look at this first row in the table. It says N2O4. So let's reduce this. Both elements can have a 2 reduced out of it. You see that? So it would be NO2. So that's my reduced or empirical formula. My molecular formula, see how the factor we pulled out was 2? If you multiplied each of them by 2 now, you've got the molecular formula. So our scaling factor is 2. It's related by a factor of 2. So that's really all that the wordiness in the box means when we have an empirical formula versus a molecular formula. So here's my reduced version. This row is telling us the scaling factor is 6. So my molecular formula will be C6H12O6. Now you might be wondering, why don't we just have one formula? Why are there 2? And the reason is because some formulas in nature, they are not reduced, okay? So they will exist like these for real. And so as a result, this is usually for covalent compounds, as a result, when we use the percent composition, we're going to find the empirical formula, but that's not the correct formula. So we will take molar mass information that's given to us to figure out what the scaling factor is. I'm going to show you how to do that with a couple of examples. So we're going to actually do a part 2 video to do the examples. Right now we're just going to talk through this concept of empirical molecular formulas, and then we're actually going to find them, okay? So bite-sized pieces here. Our next row we have Na2SO4. Now it's tempting to say this has a scale factor of 2 and reduce. However, remember that S does not have a subscript here, so it's a 1, and 1 cannot be factored down by a factor of 2. So our empirical formula and molecular formula in this case are the same with a scale factor of 1, right? It's the exact same. So if it has a scale factor of 1, nothing changes between the two. This one, however, has parentheses, so it can be, it's telling us there's 2 ammoniums, 2 carbons, 4 oxygens. So I can reduce by a factor of 2, and now I'll just have 1 ammonium, 1 carbon, and 2 oxygens. So there's my empirical formula by a scale factor of 2. If this is my reduced C2H5 and I have a scale factor of 4, my molecular formula would be C8H20. Next row, these all can be divided by 2, so my scale factor is 2, giving us CH2O. Now, what's kind of interesting to me is we have the empirical formula here of CH2O twice, but the molecular formulas are different. So it is possible, this question over here, it is possible for 2 compounds to have the same empirical formula, yes. But a different molecular formula, as long as the scale factor is different. So in this row, the scale factor is 6, so we multiplied by 6. And in this row, our scale factor was 2, so we multiplied everything by 2. So your answer for that is yes, as long as your scaling factor is different. And these two, let's finish our box and then we'll look at these last 2 questions. N3O2 with a scale factor of 2 will give us N6O2. N3O, N6O2. And lastly, C5H10, it's going to give us, we can pull out 5, so CH2O. Look, we have another one with a different scale factor. So all 3 of those have the same empirical formula, but they have a different true molecular formula. So the way that we actually figure out their scale factor in real life is using molar mass. And so if I were to find the molar mass of HC2O, I'm going to add up a hydrogen and a carbon, 2 hydrogens, and an oxygen, which ends up being, 12 to 16. I'm rounding. I know we're not supposed to do that, but I'm trying to do this quickly for you. That will end up being 30 grams per mole. For this guy, now we have it multiplied by a factor of 6. And we're going to end up having a total of 180 grams per mole. If you're not sure if I'm going too fast, take your time and break it down, pause the video, and then check. So how are these two related to this scaling factor? What's their scaling factor? Well, if my empirical formula is 30 molar mass and my molecular formula is 180 molar mass, they are related by a factor of 6. So it would be kind of like this row right here, actually not kind of like, exactly like, that we have 6 times as many of each element. So it makes sense our molar mass is going to be 6 times that. So our scale factor is 6 here. And we can find that out by dividing your molecular formula molar mass by your empirical formula molar mass. And it will give you a whole number for the scale factor. Okay, so again, that's the molecular formula molar mass divided by the empirical formula molar.